Now, what we're going to do is we're going to move on into some very common patterns that seem to pop up and take place in factoring trinomials. These patterns are very prevalent on the ACT. These are things that the standardized test makers expect you to know very, very well and expect you to recognize. So the quicker and better that you can recognize these patterns and know how to utilize them, the better. Now, the two patterns that we're going to be discussing are called a difference of squares and perfect square trinomials. Now, the first most obvious thing that we have going on here is a difference of squares is actually a binomial expression that can be split up into two separate binomials. This is different than what we did when we were factoring trinomials, where we had an expression with a trinomial broken up into two smaller binomials. Now, a perfect squared trinomial is a trinomial that is going to be broken up into two smaller binomials, but the special pattern with perfect squared trinomials is that you can get the same exact binomial for each part. So we'll look at each of these separately. We'll start with factoring the quadratic expression of a difference of squares, and sometimes called a difference of two squares. So if we look at example 3, and we're going to focus on part A, what we'll notice here is 4x squared minus 25. First of all, it's a difference of squares because it's a binomial, okay? And the word difference implies that it's subtraction. So keep in mind, this only works with a subtraction of two perfect squares. If there were addition in here, you cannot factor it. So if we had 4x squared plus 25, this cannot be factored. And we will discuss that in class in a little bit more detail as we go through this section. So keep in mind, a difference of two squares means it's got to have two perfect squares. So 4x squared is a perfect square, and 25 is a perfect square, which means it can be broken up into two smaller parts that are exactly the same. And then since it's a difference of two squares, it is separated by a subtraction sign. And so what happens in this process, and you'll notice in this pattern, is that the 4x squared can be broken up into 2x and 2x, the exact same term. The 25 can be broken up into 5 and 5, which are the exact same term. So we have two perfect squares. But what's special about this pattern is this. When we break up the difference of squares, you end up resulting into two opposite signs. So you have a 2x and a 5 for both terms, but each individual binomial, one has a positive and one has a negative. So it's very important that when you're doing a difference of squares and you break apart this binomial, you end up with two separate binomials that look exactly the same but with different signs. And so that's your first clue there on a difference of squares. Now, if I could just digress for a moment, I'll take you back up to our original problems where we were factoring out monomials. And if you look closely here at part D, you have u squared minus 4. Well, u squared is a perfect square. This can be broken up into two different u's. So that's going to go to u and u. And then negative 4, or in this case 4, can be broken up into 2 and 2. And since it's negative between there, we have a difference of two perfect squares, which means we're going to be left with a positive and a negative version of this. Now, if we're talking about the original problem, we have to keep in mind that the 4 is still a common factor, so we now have three factors if this is broken down completely to 4 times u plus 2 times u minus 2. So we factored out the common monomial first, and then we finished by factoring the difference of squares. So this is a good example of a difference of squares as well. So let's go back down to our difference of squares pattern. So you can see here that we break each individual perfect square apart, and then we break the sign apart into a positive and a negative. So that is difference of squares. Now, if we move on to perfect squared trinomials, it's very similar to difference of squares in the sense that we are dealing with two perfect squares on the outside, but we're dealing with a trinomial this time instead of a binomial. So what's going to happen here is this. We're going to break the two perfect squares apart on the outside, but what's going to happen is this time, instead of creating two different signs, it's actually going to create the same exact sign. So if we look at this, we're going to look at 9y squared and we're going to look at 16. Now 9y squared can break up into 3y and 3y, and then we look at 16, it can break up into 4 and 4. Now what I'm going to encourage you to understand, this example doesn't clarify enough, and I'll talk about this a little bit more, is that the 24y is going to break apart, and we're going to use the sign in front of the 24y as the sign in our final answer. So if we have a positive number there, we're going to end up having 3y plus 4 twice, and then we can write that answer as 3y plus 4 squared. If you notice in sample C, we have 49r squared, which breaks up into 7r, and then you have 1, which breaks up into 1, and then we have a negative value in front of that 14r, which is going to create a negative value in our final answer. Now, this is a trick or a problem that a lot of students run into. They simply only look at the outside numbers to see if they're perfect squares, and they immediately assume that it is a perfect square trinomial. Keep in mind that this pattern is very important, that the inside number is a 2 times the a value times the b value for it to work. So in this case, we have negative y squared plus 24y plus 16. If we break that up into 3y and 4 on the outsides, we must then multiply those values by 2 to get our 24 number. So that's the only way that it works correctly. If we had a situation where it said 9y squared plus 12y plus 16, that would not be a perfect square trinomial. So again, the quickest, easiest way to determine if you did this correctly or not is to see by going back and foiling the binomials to see if it comes back to the original trinomial. Now again, factoring difference of squares and factoring perfect square trinomials comes with practice. You get faster with practice, and it gets easier recognizing these patterns with practice. Again, we will spend lots of time working on these types of problems in class. So if you take this time to pause the video, there's 3 sample problems for sample problem number 3. So go ahead and work on factoring these different patterns. Okay, if we look at part A, it's clear that we're dealing with a binomial. That binomial has a negative value between the two terms. The 16y squared is a perfect square. The 225 is a perfect square. So what we have is we have 2 perfect squares being separated by subtraction. So this is a difference of squares binomial, which will allow us to break it up into 2 smaller binomials. So what I'm going to do here is I'm going to take each one separately. 16y squared breaks up into a 4y and a 4y. And then I'm going to take the 225 and I'm going to break that up, and that is going to break up into 15 and 15. So since we recognize that we are dealing with 2 perfect squares and we're dealing with a difference of squares, the pattern suggests that one of the final terms is going to be a positive, and one of the final terms is going to be a negative. And that is going to give us 4y plus 15 times 4y minus 15, and that would be your final factored expression. Now, if you wanted to double check if this were a correct answer or not, you would simply refoil this, and you can see here 4y times 4y would be 16y squared. 4y times negative 15 would be negative 60y. And then if I distributed the second term, 15 times 4y is a positive 60y. And then positive 15 times negative 15 is going to give us a negative 225. Now, in the foiling process, we had to combine like terms, and this is what makes difference of squares such a special scenario. When we refoil this, what happens here is the middle terms, the negative 60y and the positive 60y, are common. They actually cancel each other out, leaving you 16y squared minus 225, which was our original expression. So this tells us, this is our check that tells us that we factored the original expression correctly. So you can see how whenever the positive and the negative value creates opposite terms in the middle, that's what makes the difference of squares special, a special pattern in factoring. So that's example A. Now notice example B and example C are both trinomials. So here we're dealing with trinomials, and of course we're dealing with perfect square trinomials. And if we look at the outside terms, 4z squared and 9 are both perfect squares. Now the way I like to work these problems, again, I like to take each of these terms and break them up individually. So 4z squared breaks up into 2z and 2z, and 9 breaks up into 3 and 3. Now, what we need to really do is just confirm that this is a perfect square trinomial by multiplying the 2 and the 3 times 2, because remember the pattern is a times b times 2. So if I multiply 2 times 3, that gives me 6, and if I multiply that times 2, that's going to give me the 12, which is the middle term that we need. Now that I've confirmed that, I just need to get my signs right. And so you can see here that there's a negative value in front of the 12, and so that negative value actually is going to be given to both terms. So this is going to be negative 3 and negative 3, which gives me 2z minus 3 times 2z minus 3. Now, anytime you have two terms that are exactly the same that are being multiplied together, you can actually combine those terms with an exponent. So if you look, if I multiplied x times x, I could make that x squared. Well, in essence, we want to do the same thing here. I have 2z minus 3 times 2z minus 3. Those are the same terms, so I want to combine these terms together as a squared term, and this is a more consolidated view of the final answer. Now, it's extremely important that you get used to putting this as a squared term, because this will be an important process later on in chapter 5. So, perfect square trinomial breaks up into 2z minus 3 squared. And if we go to part C, we can look at part C. Again, we have a perfect square and a perfect square. So again, I like to break these up. 36w squared ends up being 6w. 20 and 6w. 25 breaks up into 5 and 5. And again, we look at the middle term. We're going to see that it's positive, but we also need to check that the 60 is correct. So 6 times 5 is 30 times 2 gives us that 60 value. So that tells us now that we can give each term the same sign as the middle term, which is a plus, which is going to give us two 6w plus 5 terms, which means we can combine those together and write it as a squared term. So 6w plus 5 squared is our final answer. And again, if you wanted to double check that any of this factoring was done correctly, you could come back and you could FOIL the two binomials that we originally factored to see if it came back to our original term. So very important that you understand difference of squares and perfect square trinomials, and that you can factor those comfortably and recognize them as they pop up. All right, now